nice proof of the law of conservation of energy, G. Fellas, be quiet, please. Thank you. Come on. Oh, there it was.
One of the fundamental principles in modern physics is that there's no absolute time. And I'm not even talking about relativity making time go at different rates if you're going at your light speed. I just mean that any time is as good as any other to set your clock to zero. The predictions of physics work all the same. It's not like there's some absolute starting time. I mean, if there were, time zones wouldn't work. In addition to allowing time zones, the fact that there's no absolute time also implies the law of conservation of energy. Here's a simple proof to show that if a force doesn't depend explicitly on time, then that force conserves energy. First, conserving energy just means that there's a certain number called the energy which doesn't change as time passes. If you compare the energy at two different times, you'll see no difference. And the total energy of a system is the sum of its energy of motion, or kinetic energy, and its energy due to position, the potential energy. So all we need is to find the change in kinetic and potential energies over time and add them up. Okay, we know the kinetic energy of an object is half of its mass times its velocity squared. So the change in kinetic energy over time is just 1/2 m times the difference of the squares of the velocities. Some clever algebra can rearrange this expression to become the average velocity times m times the change in velocity. But a change of velocity over time is just an acceleration, and mass times acceleration is equal to the force on the object. So the change in kinetic energy of an object over time is just velocity times force. On the other hand, the change in the potential energy...
So let's pause for a second. It was going pretty quick there, but that was all stuff we've seen before. It's taking the way we've written our physics equations, Madison, and just rewriting them, grouping stuff a little bit differently. Let's continue on.
The energy of an object is negative the amount of work it takes to get the object to its current position from its previous position, independent of the path taken. That is, potential energy is the negative of the force applied times the change in position. This is where the "there is no absolute time" part comes into play. You can't have potential energy for a force that changes over time. And just to be clear, no changing over time doesn't mean that an object can't experience a changing force along the course of its journey. The force might be different at different places, but at any particular place, the force must remain the same. Anyway, this is all just to say that the change in potential energy is negative F times the change in position. The negative comes from the fact that if you let the force push you along, your potential energy decreases, while if you fight in opposition to the force, your potential energy increases. So the change in potential energy over time is the negative of the force times the change in position over time. But change in position over time is velocity, which means change in potential energy of an object over time is negative velocity times force. And thus, the change in the total energy over time, which is the sum of the changes in the kinetic and potential energies over time, is V times F plus negative V times F.
What does that work out to? What's V times F plus negative V times F? So how much does energy change over time? That's the law of conservation of energy. Thought of as a different way. I proved it to you in terms of work, but you can also prove it in terms of time and energy.
Which equals zero. And zero change in energy over time is precisely conservation of energy. All for the same reason that time zones work.
Let's look at the lesson. There are different ways of looking at graphs. There are different ways two quantities can behave on a graph. Suppose we have two quantities that behave in the following manner. When x is 0, y is 0, so they go through the origin. And when x gets bigger, y gets bigger. We say they are directly proportional. Or we say y varies directly as x. This used to be big in the old math curriculum. And by old, I mean not the last one, not the one before that, and not the one before that, or the one before that. This was big in the math curriculum that I did when I was in high school, back in 87. 1987. Not that old. It's not done much anymore, Jan, but we used to always think about things in what were called proportionalities. So we would write this, y, and then the symbol for is proportional to was a little fish. x. And we would have read that as y is directly proportional to x. When x gets twice as big, y gets twice as big. When x gets 4 times smaller, y gets... If x is becoming negative, y is becoming negative. You have seen this written differently. You've seen it as an equation as y equals mx plus b, but b is 0 because I said that goes through 0, 0. You think of it as a slope. So I wrote down here, we write y is proportional to x, or if we wanted to turn it into equation, we didn't use a letter m for slope, we used a lowercase k for constant, because this was done, I think, initially in some German-speaking math, and in German, the word for constant starts with a k. So we would always say y equals kx, and k was the constant of proportionality. You do not need to know this part, but this next stuff is going to be handy. Did I spell proportionality right? I think I did. Yeah. Here's what I want you to realize. As a graph, it's going to look like that. Might be steeper, might be shallower, could be negative below the x-axis, but it could not start up high and go down because it has to go through 0, 0. And the slope of this graph, which you use a lowercase m for, it's also the constant of proportionality. You've been doing this all the time in physics. Here's a great example. D equals VT, if A is 0. V would be the constant of proportionality. What is the question it asks, Jan, at the bottom of the graph, starting with the word what? This is the trick I want to give you. For the remainder of this year, I will often give you a graph you've never seen before, and I will say to you, hey, tell me what the slope means. You can try and memorize every graph under the sun, Maddie. No. Instead, here's what I'm going to say to you. You've all learned slope is what over what? Loud and proud. You've all learned slope is what over what? Everybody, loud and proud. You've all learned that slope is what over what? Rise. You've memorized that. Okay? So, what's the slope of this graph? There's 2 ways I could think about this. I could look at the variable on the y-axis. Sarah, what's the variable on the y-axis? What are we measuring? What's the variable on the x-axis? What are we measuring? And I might know of an equation that has distance and time in it. I don't off the top of my head because I haven't emphasized that with you. Flip your phone over. What are the units on the y-axis? What are the units on the x-axis? I'm using the idea that slope is rise over run. Now I'm saying, you know what over means? It means divide. And you can either divide the variables or you can divide the units. I recognize those units. Sarah, what is meters per second telling me? Speed or velocity. Even if I didn't have this equation, if you asked me, hey, what's the slope of a distance versus time graph telling me? I could derive it by looking, in this case, at the units. Sometimes I'll figure it out from the variables. That'll be more obvious. Sometimes I'll figure it out from the units. And it's divide because everybody, slope is what over what? Over run. Rise, over, run. I don't know if in chemistry you're required to memorize what certain graphs are. In physics, they used to ask on the provincial every year students to interpret a graph. And I had kids that would try and memorize them all until I finally said, no, do yourself a favor. If it's asking about the slope, I guarantee you'll be able to figure it out by either dividing the units or dividing the variables. By the way, as a number, what's the slope of this graph? Well, I think the rise is 5. The run looks like it's 10. In your head, Jan, what's 5 divided by 10? 5 divided by 10 is not 2. 10 divided by 5 would be 2. Really? Okay. It's what I like about you. You're not too willing, you're not too humble to reach for the calculator. What'd you get? 5. Yes. And the units would be meters per second. And I would say, you know what? I know the slope of this graph is speed or velocity, and you didn't need to tell me. There's a second possibility. If it doesn't go through the origin, but when as x gets bigger, y gets bigger, we say there is an, not indirect, partial variation. I'm not going to ask you that word. But what it does mean is you can write y depends on some constant times x plus a y-intercept. Now, you never saw it written that way. What does that look an awful lot alike from your Math 10 days? And I know your Math 10 was during COVID, and so I completely understand why rise over run wasn't drilled into your brain the way it would have been. That's normally something the kids just puke out without even thinking about it. It's almost a reflex. Slope is what? Rise over run, Mr. Dewick, is what they normally say. What does that equation look an awful lot look alike? Slope-intercept form. Yeah. They're basically different ways of thinking the same thing. So, here's my question. On the y-axis, Lena, what are we measuring? And what variable? What letter? Above the meters per second. V, which stands for velocity or speed. On the x-axis, what are we measuring? So here's my question. What's the slope of a velocity versus time graph? I don't know, but I can figure it out. I can figure it out either by going v over t. That doesn't look familiar to me very much. Or I can figure it out by looking at the units. Meters per second per second. Oh! What was meters per second per second? First of all, we never wrote it that way. We wrote it as meters per second what? What must this be? What is this slope telling me, Lena? What's meters per second squared measured in? What's measured in meters per second squared? Starts with letter A. You got it? Yeah, it's acceleration. I don't need to memorize it. If you give me that graph and you say, what's the slope mean? I can figure it out either from the variables or the units. I know it's an acceleration, and if you want it as a number, it looks like the rise is 3. Yes? And the run is 10. In math, we would leave it as a fraction. Do we leave our slopes as fractions in physics? Have you noticed we like decimals? So we probably would have written it this way. The slope of this graph is 0.3 meters per second squared, and I know that's an acceleration. Do I need to memorize that? That the slope of a velocity versus time graph is the acceleration? I think all of you could have derived that. Oh. Quinn, what's the y-intercept as a number? What does it mean?
Where it starts off from?
What did we call where it starts off from in this case in terms of our physics concepts? First of all, it's a y-intercept, so is it a velocity or is it a time?
Velocity.
What do we call the velocity where it starts off at? Yeah, you know what? The y-intercept is actually telling me VI. I don't know if you all remember, those that had me last year, when we did physics, we did Unit 1, which was sig figs, scientific notation, unit conversion. Then I skipped Unit 2 and went to kinematics. Unit 2, I used to do a big lesson, a big unit in Physics 11, basically called Graphs Mean Stuff. And it was teaching people these tricks, because graphs do mean stuff. Unfortunately, in math, all you learn is that a graph is a shape. It's an equation. Actually, no. Graphs have meanings when you're using actual data. So this tells me, this y-intercept tells me VI, which is useful. Hey! What would the area underneath this graph be? You're awake now. Okay. So trick number 1, if it asks you to interpret a slope, slope is everybody. What over what? What does the word over mean mathematically? Divide the variables or divide the units. And I guarantee 99% of the time you'll be able to figure out what it means. How do you find an area? What's the area of a rectangle? Did you say times? What's the area of a triangle? Base times. You know what? Anytime you're finding an area, which mathematical operation are you doing? Not dividing. What are you doing? So if you ever want to interpret the area of a graph, you don't divide the units or variables. What do you do instead? Okay. So I would first of all try going v times t. I think maybe I know what that is. Or I would try multiplying the units, meters per second times second. Oh, Cohen, is that second one, the units, is there an S on the top?
Yeah.
Is there an S on the bottom?
Yeah.
So, Captain Obvious, what do we measure in meters? What's the area underneath this graph telling me? Probably a displacement or a distance. Oh, and in fact, what's our big equation for distance? D equals what plus a hat what? What's the equation, Cohen? Stop. There's the VT. Plus what? Oh, I guess in this case, I can even assume that A is 0. Oh, no. A is not 0. You know what the acceleration is? 0.3. I could maybe pull out that whole equation from there if I needed to. I'm not going to ask you to go that far, but there's a very good chance in the future on tests, often just as a little one-mark multiple choice question, I'll show you a graph you haven't seen. It'll be the topic that we've been looking at in that unit, and I'll say, hey, what do you think the slope of this graph is actually telling us? Or what do you think the area underneath this graph is actually telling us? Oh, put your pencils down and look up. It's going to work.
Let's take a triangular prism and lay a string of gold beads on top of it. What do you think will happen when we let go of the string? Here are three options. A, this side has more beads, so the string will slide to the left. B, this side is steeper, so it'll slide to the right.
Sorry, I was trying to plug in my keyboard so I could turn the volume down because I've got this too cranked. So let's do it this way, Mr. Duke. There. So, here's our riddle. When we let go of those beads, what will happen? Possibility number one.
This side has more beads, so the string will slide to the left. B, this side is steeper, so it'll slide to the right. Or C, the string will stand still.
I'm not going to have you vote. Actually, all three of those seem like they could work. So how could we handle this? One way would be to answer this in terms of conservation of energy.
Here's what really happens. The string stands still. One way to prove it is by calculating the forces on both sides of the string, which shows that they are equal.
And we totally could do that if we knew the angle theta, if we knew the mass of each bead, we could find the total mass on each side. It's an Atwood machine on a ramp. We did that. But there's a more clever way.
But there is another way, a way that relies on nothing but common sense. Let's assume for a moment that the forces are unbalanced. Say the left one is stronger. Now, let's attach an additional string from below. Our string is now a closed loop. The lower part is perfectly symmetrical and exerts equal forces on both sides, but the upper part is still unbalanced. As it slides to the left, the string will start rotating.
In fact, it would go faster and faster and faster.
This is a perpetual motion machine.
Is it possible for it to go faster and faster and faster and faster and faster? That would violate the law of conservation of energy because it would be gaining kinetic energy from nothing. It's, as he said, a perpetual motion machine.
It never stops, and it can perform useful work without any energy source. This cannot be true, of course. The string must remain motionless.
Is that okay? Next page over. So I've said to you, Alice, what? If it's a slope, you can figure out what it's getting at by dividing the units or dividing the variables. If it's an area, you can figure out what it's getting at by multiplying the units or the variables. Come on, Mr. Duick. Good stretch. So, third possibility. Suppose when x gets bigger, y gets smaller. We say y varies inversely as x. And we would say, don't write this down, y was proportional to 1 over x. Or y equals k times 1 over x. You don't have a clever graph version of y equals mx plus b for this one because in your math curriculum, you just haven't done this graph that much. But here's an example. Who remembers what does I stand for as an abbrev? You learned this in Science 9, but you might have been interrupted by COVID. Otherwise, I'll go to my international students because they know more than you. What does I stand for? Francesco?
I don't know to say.
What does the A stand for as units?
Ampere.
Amps. What do we measure in amps? Current. What does R stand for? Anybody remember from your Science 9 days? Yeah, resistance in ohms. So here's the question. What would the area underneath this graph mean? Now, to calculate the area, because it's a curve, you need calculus. And in fact, those who are taking calculus next semester, in the final part of the course, you'll learn how to do areas of curves and volumes of curves. It's a whole series of calculus. I don't want the answer as a number. I want the concept. Does this want me to find the area, or does this want me to find the slope? Area. What mathematical operation will I try for the area? The first thing I would do is I would try multiplying the units, I times R. International students, ignore this for a second, but the rest of you, does anybody remember what I times R is? You learned this way back in, I think it's Science 10 now, technically. Electricity. Anybody remember? Okay. International students, and remember what I times R is? It's voltage. Do you remember V equals I times R? Now, you might have been interrupted because of COVID, and so you might not have got to this. If you were in my junior science class, of course we would have played with electricity. I would have brought up my electric shock game. By the way, we will be doing electricity in the second half of this course, and yes, I'll bring up my electric shock game. Okay? Again, my point is, Clody, you don't need to memorize a bunch of graphs. If you're trying to figure out an area, multiply the units or the variables. In this case, I multiplied the variables because I figured most of you wouldn't know what an amp ohm was, but you might know what I times R was from your... Did you all see that once before? Is that vaguely familiar at all, or did you lose that during COVID? Raise your hand if you've seen that before at least once, just so I know. Okay, so some of you didn't get to it because this was probably when you were on the quarterly system. Yeah. All right. So what would the area underneath this graph be? Voltage. The last one. Y can vary as x squared. This one you have done in your math classes. It's the good old parabola. And you spend an entire unit looking at y equals a bracket x minus p all squared plus q, or whatever letters you use for that. And you learn how to flip the parabola, you learn how to slide it around, to stretch it, etc. So here's a graph. Kinetic energy on the y-axis, speed on the x-axis. What is the kinetic energy equation? Maddie? Go ahead. You said it. I read your lips. Half mv what? Of course it's a parabola. Oh, you know what the slope of this graph would be? A half m. Because if I go ke divided by v, I guess I'm left with point. This was a question one year. Well, I'll show you. Next page. We could straighten this out. Instead of graphing kinetic energy versus speed, we could graph kinetic energy versus v squared, and then it would be a straight line. What would the slope of this graph be? Well, if I go ke divided by v squared, the slope of this would be half the mass. They gave this as a provincial exam question one year. They gave the kids this graph with numbers, and they terrified kids, Nick. They said, oh, what's the mass of the cart that we're pushing? And people freaked out. No. Relax. It's either going to be the slope or the area. In this case, it's the slope. So, on some tests in your future, you will be asked to interpret a graph. To figure out what quantity is represented by the slope, which mathematical operation? Divide either the units or the variables. You'll figure it out. If it asks you to say what's meant by the area, what's the area telling us? What mathematical operation? Your homework is the take-home quiz. Your homework is the ultimate review. And bear with me, I need to show you the physicist's eulogy, but I'm going to pause the video first.